y1, y2 prime minus y2, y1 prime, but this is exactly the Wronskian. So what we've just shown is that the derivative of the Wronskian is equal to the ratio of the coefficient functions minus a1 over a0 times the Wronskian again. But this is the kind of differential equations you guys are solving on your quiz right now. It's a first-order differential equation in the Wronskian. We can separate and integrate to solve that thing. See, dw dx is equal to a1 over a naught times w. W here is just a function of x. Separate, integrate, and we get Abel's formula, which says that the Wronskian of x is some constant times the exponential of the integral of the ratio of these coefficient functions. So you think about it. If the Wronskian is 0 at one point, what happens? What does it force you to put c equal to? If the Wronskian is 0 anywhere, that forces this constant to be 0 because the exponential is non-zero. And on the flip side, if the Wronskian is non-zero anywhere, that forces that constant to be non-zero and the Wronskian to be non-zero everywhere in the domain of definition. And so Abel's formula is special to solution sets because it involved using the differential equation. So for differential equations and testing solution sets linear independence, we have this wonderful thing called the Wronskian, which is also related to the coefficient functions by Abel's formula. This does not assume that a1 and a0 are constant. They could be functions. The derivation did not assume they're constants, right? And so it's just quite a beautiful thing. Now you're like, well, that's great, but you stated the theorem up here for order n. You just gave me a proof for n equals to 2. What about n equals to 3 or 4? How do you know this is true for higher n, right? Well, I'm glad you asked, because you can generalize the calculation I just did for an arbitrary order problem. You just have to look at the Wronskian defined in terms of the determinant formula I shared with you, use the n-fold product rule, like so, and regroup some terms, do some tensor calculus, and after the dust settles, you'll again find your way back to the same stupid thing, that the derivative of the Wronskian is minus a1 over a naught times w. This is also true for the nth order problem by a similar but much more technical calculation. All right? So Abel's formula is general, and that's why that theorem is true. And finally, that brings me to the punchline, where we're nearing the punchline for today, which is that if we're solving the linear differential equation L of y equal to f, if that's an nth order linear differential equation on the interval I, then we say that the set y1 through yn is a fundamental solution set, all right, if the following is true. If, first of all, this set of functions is linearly independent, all right, and each one of these has to actually solve the homogeneous equation. So you got to be aware here, guys. This is the terminology we use. The differential equation I'm interested in solving is L of y equals to f, right? Homogeneous solutions are actually technically not solutions to the differential equation itself because they don't output the f. Like f could be non-zero. So you're plugging in y1, y2, yn, and you're getting out 0. So those are like, they're related to the problem we're trying to solve, but they're not necessarily themselves solutions. That's why we call them homogeneous solutions. Technically, a homogeneous solution is a solution to a related differential equation to L of y equals to f. But if f is equal to 0, a homogeneous solution is also a solution. But often the times it's not the case. So again, to reiterate, fundamental solution set is a linearly independent set of solutions to the corresponding homogeneous problem. Right. And this is the theorem. If we have an nth order linear ODE with continuous coefficient functions on an interval I, then there exists a fundamental solution set. This tells us what we're looking for. As we're trying to solve the nth order problem, we're trying to find n functions which are linearly independent and solve the homogeneous problem. If we can do that, we have found the fundamental solution set. That's not quite the whole story, but we're getting there. Now, how do you prove that? You actually use the existence and uniqueness theorem, and you fit the following set of data. So like y1, I make position 1 at x naught, and the velocity, the acceleration thing I don't know the name for, n minus 1th derivative at the x naught is 0. Like this is a set of initial data, we can fit it, right? By the existence and uniqueness theorem I stated at the start of the projection. And then you can find a y2, which makes the velocity 1, but the position 0 and the acceleration 0 and the rest of it. And you can keep playing this game, and you can find solution that fits initial data, which basically matches with the standard basis, E1, E2, ... En, if you know what that is. And so if we pick these solutions, which we're allowed to pick by the existence and uniqueness theorem that fit this given initial data, then when we calculate the Wronskian at x0, we plug in x0 to the functions and their derivatives, and by construction, this is 1, 0, ... 0. This is 0, 1, ... 0, and finally leading to 0, 0, ... 0, ... 1. Now, if you've had any linear algebra, you know the determinant of this matrix. This is the identity matrix. It's the matrix which plays the role of 1 for matrix multiplication. And the determinant of this is 1. And that's non-zero, which shows you that what? If we pick our solutions, y1 through yn in that way, we have linear independence of the solution set, and consequently, we have constructed a fundamental solution set to the problem. All right. There was a time in my life I used to write these things out on the board, and this lecture would have sort of like gone into about 2.5 lectures. You are much happier for me doing this, are you not? Yes, I think so. All right, so next order of business, what's the general solution of the homogeneous nth order problem? So homogeneous problem means that that this is 0, right? Well, fine. All right, great. I could have put 0 here to start with. I don't know, whatever. Anyway, so L of y equals to 0 can be any solution of L of y equals to 0 can be expressed as a linear combination of the solution set. That is, there exists constants C1 through Cn such that that's the solution. So for a homogeneous problem, once we find our fundamental solution set, we're done. In other words, returning to the example I talked about sine and cosine over there, sine and cosine are linearly independent. Y prime prime plus y equal to 0 is a second order problem. Therefore, C1 cosine plus C2 sine, that is the general solution to that problem. Our intuition was correct, and it is verified by this theorem. All right? Now, here's the proof, which I guess I don't know if is it worthwhile? I don't know. Let's see here. Proof. Suppose we got a fundamental solution set of L of y equal to 0. We want to find constant C1 through Cn such that y is equal to that. So I'm supposing I have a solution, right, to L of y equal to 0. Suppose y is a solution. If y is a solution, we can pick a point in the interval of definition, and we can calculate the value of y at x0, the value of y, the derivative of the solution at x0, and so forth. We can calculate the initial data, which has to be matched, right? So for any solution, you know, you give me a solution to the problem, I can take that solution, I can evaluate it at a point, its derivative, its acceleration, all the way out. That gets me a set of data, right? And then I can do what? So then what I'm trying to do is I'm trying to find C1 through Cn which match that linear combination to the given y. And so if you look at that, that becomes solving the problem of solving these n equations in n unknowns, right? So these are given. These are also given because we're given a fundamental solution set, and we're just trying to find the C1 through Cn. But this has a unique solution because guess what? This is the Wronskian of the fundamental solution set, which is an invertible matrix. Well, that's not the determinant of this is the Wronskian, but the point is that this matrix has a determinant which is non-zero, which means it can be inverted, and we can solve for that. So you're like, it seems like you need linear algebra to really understand differential equations. Yes, it's true. You got me. I don't deny it. And finally, what about the non-homogeneous case? Well, here's the kind of interesting thing. If we have a non-homogeneous problem, and we got a fundamental solution set, which again is homogeneous solutions, and if we have any solution to the non-homogeneous problem, L of y equal to f, then we can express any general solution as the linear combination of a particular function, yp, which solves it. So p is for particular. That just means it's a specific function, all right? So L of yp equals f. We can take that particular solution and add it to this linear combination of the fundamental solution set, and that will be that will allow us to match to the given solution. So this is the general solution to the non-homogeneous problem. So just to set a path forward, we see that in order to solve the non-homogeneous problem, we need to first solve the homogeneous problem. Because if we can solve the homogeneous problem, that will allow us to find this piece of the solution in general, right? Once we figure out how to do that, then we'll return to the task of how to find the yp. That's the non-homogeneous problem. Going forward, we probably spend maybe 80% of our time working on how to solve the homogeneous problem. And then after that, we'll probably spend the last 20, 30%, wait a minute, the rest of our time on the non-homogeneous problem. This is just some examples of it. And that brings us to operators in calculus. So this is what I'll do next time. I will build a machine that will solve any constant coefficient homogeneous differential equation. Here. I know you guys are worried because the rain is pressing outside. I know it's really, I can hear it on the roof. I mean, that would be hard. We're in the second floor, but just pretend with me for a second for the purpose of this joke. And can you turn the light on for me? So check it out. If I was going to solve, say, y prime 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 minus y equal to 0, all I do is look, so that's like d to the fourth minus 1 acting on y equals to 0, and then I can factor that. That's d squared plus 1 times d squared minus 1 acting on y equal to 0, which is, by the way, d squared plus 1 times d minus 1 times d plus 1 acting on y equal to 0. And once I have that, the machine I will build next time will tell us to write down y equals to c1 cosine of x plus c2 sine of x plus c3 e to the x plus c4 e to the minus x. And there you go. That's the general solution. So that is a fourth order constant coefficient differential equation I just made up and solved in the last 30 seconds of class. That is what next lecture does for us. It gives us a machine which will efficiently and quickly kill any such problem. Much easier, in fact, than what you've been doing for the first order problem. I would argue this, I mean, algebra, you got to come to terms with, but when you get right to it, once you learn it, it's much easier than the first order problem even. But there is much to learn. Anyway, thanks guys. Happy hurricane to you all.